What's up, guys? It's me, Sir Ernest, and today we will discuss a sample problem related to Hamiltonian dynamics. The problem reads: consider a plane pendulum consisting of a mass m attached to a string of length L. After the pendulum is set into motion, the length of the string is shortened at a constant rate. That is, the that constant rate a dl dt is negative alpha, which is a constant. The suspension point remains fixed. So compute for the Lagrangian and Hamiltonian functions and compare the Hamiltonian and the total energy and discuss the conservation of energy for the system. Okay, so first let's try to draw the problems here. Okay, so if you have a simple pendulum where this is your support and this is the mass and this is your length, and then if this is your vertical, let's say this is your theta. Okay, so notice that it's mentioned here that the length of the pendulum is actually a function of time. Okay, so if we're going to set this as our reference point or reference height, this will be our h. Okay, so let's try to consider the problem now. So as previously discussed, for a simple pendulum, it's better to choose the polar coordinates so that in polar coordinates, the kinetic energy is equal to 1 of m times L dot squared plus L squared theta dot squared. Okay, while the potential energy is equal to mgh, which is equal to negative mg h will be L cosine theta. Excuse me. Okay, so therefore, you already know, or we can rewrite the Lagrangian to be equal to 1/2 m L dot squared plus L squared theta dot squared minus negative, so that's plus mgl cosine theta. So this tells us that the Lagrangian is a function of L, L dot, theta, and theta dot. And these are all functions of time. Okay, however, so it's very tempting to write the Lagrangian this way. But as mentioned here, the derivative of L with respect to time is a constant. And what is this? This is actually your L dot. Okay, so that means L dot is not a function of time. So this way, so that means the dependency of the Lagrangian with L dot, where L dot is supposed to be a function of time, is not the case here. So that means we should write the Lagrangian as follows. So we know that L dot is equal to negative alpha. So you square that, that's alpha squared. So that means the kinetic energy should be written as 1/2 m times alpha squared plus L squared theta dot squared plus mgl cosine theta. So now we are reduced to a Lagrangian that is a function of L, theta, and theta dot. And these three variables are all functions of time. Okay, So now, let's compute for the generalized momenta so that we'll be able to calculate our Hamiltonian. So the generalized momenta is now written as would be PL, which is the derivative of L with respect to L dot, which is equal to 0 as shown here. Whereas P theta will be equal to the derivative of the Lagrangian with respect to theta dot, and this is equal to m L squared theta dot squared. Okay, so from here. Now, so this equation or this result tells us that theta dot is equal to P theta over ml squared. Okay, so this tells us that the kinetic energy, therefore, can now be written as 1 of m alpha squared plus, so that's 1 half ml squared times p theta over ml squared, so which gives us the form p theta squared over 2 m l squared. Okay, so from here we can now rewrite our Hamiltonian. Okay, let me move it here. Okay, okay, now the Hamiltonian okay, sorry about that. Okay, so the Hamiltonian becomes H equals P L L dot plus P theta theta dot minus L. So we already know that L dot is 0. So now this is now equal to P dot times theta dot. So this is P theta squared over ml squared minus the Lagrangian, which is this okay, plus minus of this, so this is minus mgl cosine theta. So therefore the Hamiltonian will now be equal to p theta over 2 m squared. So this minus this is this minus 1 of m alpha squared minus mg cosine mgl cosine theta. Okay, so this is your Hamiltonian and this is your Lagrangian. Now let's compare the Hamiltonian to the total energy. So we know that the total energy will be kinetic plus potential energy. And this is now equal to 1 half m alpha squared plus p theta squared over 2 m squared plus u is minus mgl cosine theta. So as you will notice that H, or your Hamiltonian, is not equal to the total energy. Okay? And that's because so that means the this equation, this result the L in this case changes with time. So in other words, there's an implicit dependence on the velocity with regards to your potential energy. Okay, so also you know that H, the total energy, is equal to this. Okay, because it's mentioning that L changes with time, so this is a function of time. So therefore, the total energy is also a function of time, explicitly. So therefore, energy is not conserved. Okay? So to summarize, the Lagrangian of the system and the Hamiltonian the system tells us that so this is the Lagrangian of the system and this is the Hamiltonian of the system, and we showed that the Hamiltonian is not equal to the total energy of the system. Also, because of the fact that L is a function of time, so remember that derivative of L with respect to time is negative alpha. Okay, because L changes with time, so that means the potential energy changes with time as well. So the potential energy changes with time as well. That means the total energy of the system changes with time. Therefore, the energy is not conserved. Okay, so that's it. So this ends our solution to problem 7.24 of Thornton and Marion. So thank you for watching. I hope you learned something today, and I will see you again in the next video. Bye bye.